Hello, my name is Wenli. I'm from Department of Physics, University of Alabama at Birmingham. This talk is part of the CAMCSE workshop. In this talk, I would like to give you a discussion on, give you an introduction on diamond anvil cell, the most popular used technique to generate static high pressures. Then I move on to discuss several characterization techniques under high pressure, mostly in diamond anvil cell, including electrical resistivity, AC susceptibility, and a few synchrotron X-ray methods. The diamond anvil cell is a very simple mechanical device. The physics principle is just the fourth divided by the contact area A. So to increase the pressure range, the diamond's flat area here at the tip is typically reduced to the order of 50 micron to a few hundred micron size. So that gives you the typical sample size about 20 to a few hundred microns. You can see here there are two major components, two opposing diamonds pushing against each other, and between the diamonds there is a metallic gasket to isolate, to separate the two diamonds and also form a sample chamber. It's typical to use pressure transmitting medium here, and with your sample positioned at the center of your gasket hole. It's also common to use ruby as a standard to measure high pressure, measure the pressure value inside the sample chamber in situ. So I'll come back to the ruby fluorescence in a minute. The diamond anvil cell has, the cell body is typically made of hardened steel alloy. Shown in this picture is a symmetric type diamond anvil cell. There are two major components of the cell body. So this piece here, a piece look like a cylinder, and a cylinder piece and a piston piece. The diamond is sitting on top of this diamond seat, typically made of tungsten carbide, as a supporting material. So when you assemble the diamond anvil cell, the piston piece is a slide into the cylinder piece, and this is how it looks like when it's fully assembled, with the screws along with the washers already assembled in the cell. So the structure of the cell typically has an axial port allowing to align the diamond anvils and take measurements, optical measurements, as well as X-ray measurements along the axis. And there is also axis port on the radial direction. So this axis port here on the side allow you to do radial X-ray diffraction or other type of measurements, such as X-ray fluorescence. So as shown in this symmetric type diamond anvil cell, the pressure is achieved by tightening the 4 screws here. But this method becomes inefficient when you do some type of measurements, for example, cryogenic conditions. Each time, if you need to change the pressure, you will have to warm up the sample to room temperature and tighten the screws. So another way to change pressure is through this gas-driven membrane. So here is an example of the gas membrane can with the membrane already assembled. So the cell will be sitting inside the can along with this gas membrane. So this capillary here allows to apply high pressure gas into the membrane. So the high pressure gas would deform or expand this membrane, and this expansion is translated to the diamond and apply pressure on the sample space. Another method to change pressure in situ is using this gearbox. So this gearbox basically tightens the 4 screws directly, or loosening the screws to decrease pressure. Again, for low temperature measurements, very often when the temperature is changed, the pressure also changes because the cell body contraction. So this so-called double membrane design allows you to compensate the pressure change as the temperature is varied. So this is an example of a typical symmetric cell. And this membrane C here is just a regular membrane shown here, similar to this. And a second membrane, A, is added so that when the pressure is increasing as the temperature is decreased, you apply membrane pressure in the membrane set A to push open the piston and the cylinder, so the pressure can be stabilized at different temperatures. So this is very important and useful when you need to do temperature measurements over a very wide temperature range. Another key element in the diamond anvil cell is the pressure transmitting medium. There are 3 types of pressure transmitting media typically used, 3 different forms: liquid, for example, silicon oil, Daphne oil, methanol, ethanol, and gas pressure medium, helium, neon, argon, nitrogen, and so on. And solid medium, typically sodium chloride, or MgO, or steatite. To load the gas, high pressure gas, into the sample chamber in the diamond anvil cell, a gas loader is typically needed. Here, this picture is an example of a gas loading system located at the JC cars at the Advanced Photon Source of the Argonne National Lab. The choice of pressure medium can vary, depends on the hydrostaticity of the high pressure environment for your sample. This paper here is a great guideline, provide a great guideline for picking the right pressure medium under pressure or at the low temperatures. It's important to know what exact pressure has been applied in the sample chamber. So to measure the pressure, if you have X-ray diffraction, if you have access to X-ray diffraction, a common way to better determine the pressure is to use a known standard material, for example, platinum, gold, copper, neon. In case of neon, is used as a pressure medium, or rhenium if rhenium is used as a gasket material. Another popular way of measuring the pressure is using ruby fluorescence. So in ruby fluorescence measurements, the chromium energy levels in the host material, aluminum oxide, can be excited by the right excitation wavelengths, for example, green laser or blue laser. Or in this case, LED source is used to excite the ruby fluorescence lines. So this ruby fluorescence, there are two characteristic lines, R1 and R2. Both R1 and R2 lines shift under high pressure, and this shift has been calibrated by many groups. A most recent pressure calibration is reported in this paper here in 2020. So this ruby pressure gauge described here in this equation becomes more and more popular. So ruby fluorescence is great for measurements below 100 GPa. However, as the pressure is increased, the ruby fluorescence intensity tends to decrease. Around 100 GPa also, it's really difficult to measure the ruby fluorescence. So another approach developed over the years is to use the diamond anvil Raman gauge. So in the diamond anvil Raman spectrum, there is an edge that show up under high pressure. Is related to the stress on the diamond anvil that's used to achieve high pressure. So this Raman edge has been calibrated against known standard up to 410 GPa. The calibration is shown here reported in this papers. So in this calibration, there is this V0, which is the diamond Raman edge frequency at ambient pressure. And delta V over V0 is the relative Raman frequency change. So you just need to take a diamond Raman spectrum and determine the edge frequency and plug in this equation to calculate the pressure on the sample. Diamond anvil cell come in with many different designs for different applications and sample environment. This picture is just a collection of part of our diamond anvil cells. For example, here, this is a typical so-called BX90 cell that's commonly used for single crystal X-ray diffraction. I'll come back to this in a minute. And this is a typical symmetric type diamond anvil cell. And these three cells are made of copper beryllium. That's excellent for high field measurements or magnetic measurements. This small cell with two truncations are used for nuclear resonance scattering that goes into this custom designed cryostat fabricated by DAC tools. And this small panoramic cell is also used in this experiment where you place the two avalanche photodiode detectors next to the diamond anvil cell and collect inelastic X-ray data under high pressure. Here, this is a picture of the Dyer cell developed in U Chicago. This cell can be used in PPMS, and you can see here there is a gas membrane that can change the pressure on the diamond inside the diamond anvil cell in situ. This is a typical large panoramic cell, just a bigger version of this miniature panoramic cell here. And this cell here is a slight modification of the panoramic cell, has 4 different windows, allow you to take data from the axial direction. When you consider the different applications and sample environments, you need to first think the requirement of the experiment and how the measurements is done and what kind of material that should be used for the diamond anvil cell construction. For example, again, if you do high magnetic field measurements, a non-magnetic cell body is preferred. And also a gasket material is equally important. Typically stainless steel, uranium, or tungsten are used in many experiments. However, if you want to do measurements along the axial direction, for example, radio X-ray diffraction or fluorescence measurements, beryllium gasket is typically used. In some cases, when you need to go to very high pressure, beryllium is very soft, and cubic boron nitride combined with epoxy can be used as an insert to increase the sample thickness. In experiments such as electrical resistivity measurements, a non-metallic gasket is required to insulate the gasket from the gasket to the electrical probes. So very often you start with a metal gasket, for example, stainless steel or uranium, and then add an insulating layer on top of it. Another concern is the choice of diamond anvils in many experiments, especially if you do X-ray absorption in the transmission mode. That's shown here. In the transmission mode, you shine the X-ray along the diamond anvil cell axis and then take data in the downstream in the transmission. So the X-ray absorption by the diamond anvil can be significant at low energies. As shown in this figure here. For example, a typical diamond thickness of two diamond anvils is about 4 millimeter tall. The 4 millimeter thick. You can follow this curve, the black curve here. If you are doing measurements with energy below 10 kilo eV, the absorption by the diamond anvil cell are significant. So in this case, a typical practice is reduce the diamond thickness by perforate the diamond. So in this, the first example here, you use a partially perforated anvil on the top, and the bottom diamonds are a combination of a miniature diamond anvil plus a fully perforated anvil. So this partially perforated anvil very often leaves with only 100 micron thick of diamond left, and this miniature anvil is roughly 700 micron thick. So this way, instead of 4 millimeter, the X-ray beam only see less than 1 millimeter of diamond anvil to reduce the absorption. Another scheme is a different combination. You use a full anvil, which is typically 2 millimeter tall on one side, and another side use a partially perforated anvil with about 100 micron diamond left. As shown in this diagram here, the diamond anvil cell applications is extremely broad, and can be combined with synchrotron X-ray in many disciplines. So there are many, many different types of synchrotron X-ray techniques can be integrated with the diamond anvil cell. For example, X-ray diffraction, X-ray spectroscopy, absorption near edge, or XFs, or XMCD, or partial fluorescence yield, X-ray imaging, X-ray inelastic, X-ray inelastic scattering. The diamond anvil cell is also compatible with different sample environments. For example, in the superconducting magnet of different design, and in low temperature applications with helium flow cryostat of different design, and can be also used for heating experiment. This is example external heating, and here shows resistive heating. It can also be used in laser heating experiment to study melting or work on synthesis under high PT conditions. Of course, it can be also used in a closed cycle cryostat, in this case, PPMS, that can be used in many studies at combined low temperature and high magnetic field conditions. In the next section, I plan to discuss the characterization techniques under high pressure. The first method commonly used in material studies under high pressure in diamond anvil cell is the electrical resistivity method. The first picture shown here is a typical setup of 4 probes made of either platinum foil or wire, or gold wire or foil, extended into the sample chamber. The second picture shown here shows the layout of the 4 probes for van der Pol measurements and a piece of sample loaded. So this type of preparation is fairly challenging because it requires very steady hand to lay out the probes and the precise loading of the sample onto the 4 probes. Another method to make this type of measurements a lot easier is using the designer anvil developed here at UEB by Professor Yogeshwara's group. In this designer anvil, there are probes already fabricated onto the diamond tip, and a sample can be just directly loaded inside the sample chamber and also insulated by this pressure medium C-tight. So electrical resistivity measurements is extremely helpful to provide information on material transport properties and map up the phase diagram under high pressure. Here is an example of high pressure studies to over 1 megabar pressures in dysprosium. By tracking this anomaly in the resistance at low temperatures, one can get the information of the magnetic ordering temperature under high pressure and correlate with the different phases, crystal structural phases. Of course, electrical resistivity can be also used to study superconductivity. It's very common to induce in some cases, induce superconductivity or change the superconducting transition temperature with pressure. Here are two examples of high pressure studies using the electrical resistivity in diamond anvil cell. In the first case, a medium entropy alloy, and the second case, a high entropy alloy. As mentioned earlier, the low temperature and high field measurements can be performed simultaneously in diamond anvil cell. So the information obtained doing electrical resistivity can be very useful to understand the origin of the superconductivity in the material. Another method is the AC susceptibility in diamond anvil cell. Shown in this picture here is a coil design that was used in Professor James Schilling's group from Washington University in St. Louis. In this coil design, so there are two coils. The coil on the left is located outside a diamond, and this coil set is composed of a pickup coil and also an outer excitation coil. The coil on the right is used as a compensation purpose to cancel out the susceptibility contribution from the background. There are many beautiful experiments have been done using this coil design. Here shown in this figure here is an example of studies of superconductivity under high pressure in lithium. Of course, you can see here the filling factor of the sample is really small because the coil is relatively large comparing to the sample size. And the distance from the sample to the coil is relatively far. A few years ago, another group have developed a different coil design, such as shown in this picture here. In this design, the pickup coil is designed or constructed so that it matches the angle of the diamond anvil. So this way, the filling factor is increased, and also the sensitivity of the coil is largely enhanced. So that's demonstrated in these figures here. It has been, the same coil has been used to study the antiferromagnetic order in dysprosium up to 4.5 GPa. Another more efficient method to improve the coil sensitivity is shown in this picture here. That's also developed here in Dr. Yogeshwara's group. So in this coil, the coil set is the pickup coil is again fabricated onto the diamond anvil tip, and the sample will be loaded at the center of the diamond anvil. And you can see here, comparing to the previous two different type of designs, the filling factor is significantly increased, and the sensitivity is largely enhanced. So that's demonstrated by the measurements of several heavy rare earth metals. The magnetic ordinary temperature can be traced up to almost 20 GPa. crystal structure information is very important to determine, to understand the material properties under high pressure. And very often pressure can induce crystal structure transitions. So it's very common to do X-ray diffraction experiment to understand the modification of crystal structure under high pressure. At the synchrotron beamlines, there are two types of commonly used diamond anvil cells. The first one is a symmetric cell that discussed earlier with standard diamond anvils and also at least one cubic bond nitride seat to allow you accessing the large 2 theta angles. Another commonly used diamond anvil cell developed more recently is the BX90 diamond anvil cell, in combined with the use of Bowler LMAX anvils, as shown here. So in this design, the diamond, the Bowler LMAX anvil, is a conical shape and sitting into a tungsten carbide piece that has the matching profile. So this design, in combination with this BX90 cell, allow you to access optical angles up to 90 degrees. Before you conduct any X-ray diffraction experiment at synchrotron beamline, you definitely want to contact the beamline scientist and figure out the detailed configurations of the beamline. For example, if you plan to use the online Ruby system to measure pressure in situ, the information, the location of the Ruby system relative to the detector, typically in the downstream, is very important because you want to, for example, your Ruby system, in this case here at beamline 1222 at AOS, the optical system is in the upstream and the detector is located in the downstream. In this case, the Ruby should be loaded in the upstream side. Also, if you plan to use a gas membrane at the beamline, it's better to find out what are the compatible diamond anvil cells to the gas membrane system. There are many software packages that are useful to reduce and analyze X-ray diffraction data. So here I listed several software that are used in my group for data reduction, analysis, and visualization. After learning the crystal structures, very often in case of magnetic materials, one wants to know the pressure effect on the magnetic state. Other than the electrical resistivity and susceptibility techniques we discussed earlier, one can also use a synchrotron X-ray to probe the magnetism directly. For example, there CAMCSE, this X-ray magnetic circular dichroism technique, can be used to probe the magnetic state. And this technique is element selective. So because this technique relies on the X-ray absorption technique, and that's typically done at the element's absorption edge. Here are two examples of CAMCSE measurements under high pressure. The first example here is the XMCD of europium at the L3 edge. As you can see here, the XMCD signal increases under high pressure from 3 GPa to 21 GPa. So the XMCD signal reflects the strength of magnetization. Here is another example, nickel K edge. And in this work, the magnetism of nickel has been studied up to 200 GPa using XMCD. As shown here in this XMCD data, the magnetism in nickel is stable. It remains up to 200 GPa. Another technique is X-ray magnetic scattering. It can be resonant or non-resonant. This example here is a resonant case where you tune the X-ray energy to the iridium L3 edge in the studies of this honeycomb iridate material. By tuning the X-ray to the absorption edge of the magnetic element, the magnetic scattering cross-section can be largely enhanced. This beautiful experiment shows that above 1.4 GPa, the spiral order in this lithium iridate is suppressed. Another technique is commonly used to study magnetic state is synchrotron Mossbauer spectroscopy. This technique is isotope selected. So it's similar to the previously discussed XMCD or magnetic scattering. In that case, in those two cases, they probe the specific element, so it's element sensitive. And this technique here is isotope selected. For example, if you are concerned with iron, you are only sensitive to iron 57 isotope. So this technique not just study magnetism, it can also provide information on valence state and the local coordination, spin transitions induced by high pressure or low temperature. Here I show you three different studies on three isotopes. The first example here is on europium-151, a commonly used isotope in Mossbauer studies. The nuclear resonant energy is 21.5 keV, so this high energy is very favorable in the sense of less absorption by the diamond anvils. The second example here is in nickel 61. The nuclear resonant energy is much higher, 67 keV, and this group has studied the magnetism up to 260 GPa and found out that nickel remains magnetic at this pressure. This example here is a high pressure and low temperature studies of iron hydride. In this material, this is first synthesized using laser heating under high pressure, and then the cell was cooled down to study the magnetic transitions under high pressure and low temperature conditions. In this compound, there are two different iron sites. iron 1 and iron 2. So there's two different iron sites can be differentiated by the Mossbauer effect, because these two sites shows different magnitude of hyperfine interactions, more specifically, in this case, the hyperfine magnetic field. By tracking the hyperfine magnetic field for each side at different pressures and temperatures, magnetic information can be obtained for this two distinct iron sites. So this demonstrates this technique is extremely sensitive and it's a local probe. Another application I want to briefly mention is using the synchrotron-Mossbauer spectroscopy to detect Meissner effect. It has been applied in 2016 in the studies of sulfur hydride by using a tin 119 foil as a probe. If you want to know more information about this application, I refer you to this paper here. Thank you for watching.